For the most part, we use private IP addresses in our networks. But the internet uses public addresses. So how do we make these two work together? We need a device to translate between these two types of addresses. And for that, we have Network Address Translation, or NAT. Let's see how this works and how it's configured. Think of the header on a packet. This contains the source IP address that the packet was sent from, as well as the destination IP address that the packet is being sent to. NAT is the technology that can take an IP address in a packet's header and replace it with a different IP address. The most common use for NAT, as mentioned at the beginning of this video, is to translate between public and private IP addresses. This is part of a strategy to save public IP addresses across the globe. Decades ago, the intention was that every device would have a public IP address. However, there's a limited number of public IP addresses available, and we started using them far too quickly. So these days, we mostly all use the same private ranges in our networks. But to connect to the internet, we need public addressing. So a router between our network and the internet will translate private IPs to public IPs and back again. And if you're wondering, we will generally have public IP addresses given to us by our internet provider, and they often won't give us very many. How does this work? It's all based on the IP header. Every packet has this header which contains a source address and a destination address. A router has a set of rules about which traffic should be translated and which traffic should be left alone. When a packet arrives at a router, the router will examine the IPs in the header to find traffic that matches a NAT rule. If a packet matches a rule, then this router will rewrite the source or destination IP address in the header and send the packet on its way. We can even configure NAT to change port numbers in a TCP or UDP header if we want to, but we'll save that one for later. There are two types of NAT. These are source NAT and destination NAT. Source NAT is the most commonly used type of NAT. As the name suggests, source NAT changes the packet's source IP address. This is generally used for internet access, as we explained earlier, where we are using private IP addresses in our network. The router takes the private IP in the header and replaces it with a public IP. Devices on the internet see this packet as coming from a public IP, and they are able to send traffic back. The router will change the IP address back to a private one as the packet passes through. The alternative is destination NAT, which is a bit less common. As you've already guessed, this is where the router changes the destination IP address rather than the source IP. We might use this if two organizations have merged and they were already using the same IP space. Normally this wouldn't work as they need to have unique IPs. However, we could use NAT so each network thinks that the other is unique. This scenario is a bit complicated, so we'll leave this one alone. Some devices can translate both the source and the destination IPs. This is typically the role of a firewall which has advanced NAT features. We do have a video on configuring NAT on the ASA firewall if you'd like to see that in action. It's a bit more complicated though, but it's worth a look if you're interested. But in this video, we're only going to look at source NAT for internet access. Before we get right into the configuration, there's a couple of terms to understand. When we configure the router, we specify which interfaces are inside our network and which are outside. Cisco uses the terms local and global to describe the inside and outside. Keep in mind that different vendors will use different terms for this. When a device first creates a packet, it puts its own IP address in the header as the source. This IP address is called the inside local address. This is the real IP of the host inside your network, and it is probably a private IP. The outside IP is the destination address. This is the IP of a device outside of our network. Technically, this may not be the destination's real host IP, as NAT may change it, but this is what our hosts think is the real IP. After a packet has a NAT rule applied, different terms are used. The source IP address is called the inside global address. This is our host's IP address after it has been translated. For internet access, this is now likely a public IP. The outside global IP is still the destination address. This would only change if we configured destination NAT, which is not the case in this example. Configuring static NAT, also known as one-to-one NAT or basic NAT. A static NAT will take a local IP address and statically map it to a global IP address. These two IPs are always a pair, and the mapping does not change. We would typically use this if we had a server on our network, maybe a web server, that we want to make available over the internet. People on the internet can then access our web content using the public IP that we configure in the static NAT. The downside to static NAT is that we use up public IP addresses very quickly, as we need a public IP for every static NAT rule. Bidirectional NAT. When we think of NAT, we often need to think about where the traffic is initiated, that is, where traffic starts. For example, traffic may start on a workstation with a web server on the internet as the destination. The web server will then send traffic back to the workstation. This means that NAT is applied in a particular direction, and that direction depends on where the traffic starts. Consider the example we just configured. There is a web server inside our network, and people outside our network need to reach it. The server can initiate a connection to the internet if it needs to, or something on the internet can initiate a connection to the server. The NAT we configured will work, no matter which direction the traffic is going. This is a bidirectional NAT. The opposite of this is called unidirectional NAT, which we'll see at the end of the video. But for now, let's consider how to configure NAT for our workstations. Usually we won't use a static NAT for this, as we have a lot of workstations and not many public IPs. One option we could consider is dynamic NAT. This does not use a one-to-one mapping between a private IP and a public IP. Instead, we can create a pool of public IP addresses and let the router map an IP to each workstation as they're needed. Closely working hand in hand with NAT is port address translation, or PAT. In fact, they're so closely related, we usually just use the term NAT as an umbrella for both of these technologies. If you remember back to when we looked at TCP and UDP, you will remember that they also use headers. And in these headers are source and destination ports. Just as NAT rewrites IP addresses in the IP header, PAT rewrites port numbers in a TCP or UDP header. In most cases, PAT and NAT will work together, so one will be changing the IP address and one will be changing the port number. This is quite common when we want to make a few services available to the internet by port number alone, rather than translating the entire IP address, which exposes all of a server's ports to the internet. We need to discuss which some may consider the most important of them all. This one is called port overloading, or masquerading, or many-to-one NAT. Think of a case where we don't have many public IP addresses available to us. Maybe we've only been given one or two by our service provider. In a case like this, we can't use a dynamic NAT pool like we did earlier. This is because dynamic NAT will map one public IP to each host that needs internet access. We'll very quickly exhaust the pool of IPs, and any additional traffic will be dropped. So it's clear we need an alternative. This is where port overloading comes in. This is still a form of dynamic NAT and PAT, but the router will translate ports as well as IPs. In addition to the pool of IPs, the router has a pool of ports that belong to each IP address. There are about 64,000 ports in each pool. Now think of the first workstation accessing the internet. It sends a packet to the router, which contains the source and destination IP and port numbers. The router will rewrite the source IP with the public IP address, and it will also rewrite the source port with a port from the pool. The router keeps track of which ports have been used and which workstation is using them. This way it knows where to send return traffic. Now when the workstation wants to access the internet, it goes through the same process as before. In our example, it gets the exact same public IP as the first workstation, but it will get a different source port from the pool. In this way, devices on our network can share a single public IP address as they each use unique source ports for each connection they open. And as there are about 64,000 TCP ports and 64,000 UDP ports, we won't run out of ports quickly. NAT, where traffic can be initiated from either the inside or outside of our network. Port overloading behaves differently. This is an example of unidirectional NAT, where traffic must be initiated from inside of the network. Return traffic is fine, of course, but the connection needs to start on the inside. Why is this? Because the router builds its table of port to IP mappings dynamically as connections are needed. So if someone tries to connect to a workstation from the internet on a particular port, it's highly likely that that port is not already in the translation table.